Okay, so thanks very much for coming. So I'm going to talk about some recent work on the perceptron model, and all of this is joint work with Jianding, who is at UPenn.
I thought you were pulling my leg. I'm sorry.
That's okay. Okay, so let me start by introducing the model, which is maybe familiar to a lot of you. It's just a simple problem in high-dimensional random geometry. So the model is as follows. You start with a space which is I'll call Qn, and we'll take it either to be the plus minus cube in n dimensions or the sphere of the same radius. And then you take the space, and then you repeatedly remove random half spaces from it. And then the piece that is left over is the solution space, which I'll call S. So it comes in these two flavors. The plus minus version is usually called the Ising perceptron. And then the other version, where you start with a sphere, is called usually the spherical perceptron. And then I would be interested in a very simple first order quantity, which is how many half spaces can you put down before the whole set will become empty with high probability, let's say. I won't talk about this, but one motivation is that it's related to some toy model of a neural network that will memorize some collection of given patterns. So in that setting, the patterns correspond to the half spaces, and the synaptic weights of the neurons, they correspond to the elements of Qn. But I won't really talk about this, so I'll just focus on this simple geometric model. Okay, so let me give the formal notation. So the set S I will be interested in is the collection of vectors in Qn, which again is either the cube or the sphere, such that if I take this M by N Gaussian matrix, so the entries of the matrix will be IID standard Gaussians, and each row of the matrix, it will correspond to a normal vector for one of your random half spaces. So each row defines one of the half spaces, and then the definition of the space is that if I take this random matrix and apply it to an element of Qn, I require that this thing, when scaled by square root n, is larger than kappa entry-wise, where kappa is some constant parameter, and then in order for it to be interesting, square root n is the correct scaling. Okay, so I hope the model is clear. So this is just in more compact notation. So it's a random subset of either the cube or the sphere, which is just simply defined in this way by this disorder matrix G. Okay, so what has been studied about this model? In the physics literature, it was analyzed in the 80s, and especially in a series of works by these people. And what they found is that for the spherical perceptron, when kappa is non-negative, or for the Ising perceptron for any value of kappa, all of these cases, they have simple asymptotic. So I will say later what simple means, but formally in the physics terminology, it means that the models are replica symmetric. So I will say more about that. But essentially it means that from the physics point of view, these models are exactly solvable. And what can they say? They can explicitly compute the asymptotic size of the set. So if you take the volume of the leftover set, the exponent tends to some explicit function that depends only on kappa and on alpha, where alpha is the ratio of rows to columns. And moreover, the capacity, which is the point for this set to become empty, it's defined also in terms of this function, and it's just the point where this function in terms of alpha crosses 0. So this is the critical capacity that's predicted for these types of models. And in particular for the Ising perceptron, when kappa is 0, the critical capacity is around 0.83, and this was found by Kraut and Mézard. So what is known rigorously, so I should say in the physics analysis, when they look at the spherical or the plus-minus case, actually the analysis of the two cases is essentially identical, so they're treated in the same way. But mathematically, it doesn't seem that methods for one case can carry over easily to the other. So the kappa non-negative spherical model is pretty well understood. So Cherubina and Tirozzi computed the limiting exponent for the volume, and they showed that it matches the physics prediction. And then in a later work by Stoinich, he computed the critical capacity and also showed that it matches the prediction. And in particular, I want to mention that this is a very simple argument, essentially just a comparison of Gaussian processes. So this is a very nice proof, I think. Actually, for the case, for the spherical case, when kappa is 0, the critical capacity was found to be 2 in much earlier work by Wendell and by Tom Cover. And so one thing which is underlying these works for general kappa is that if you think about kappa non-negative, so when kappa is non-negative, it means that the half space includes the origin, so you're cutting off more than half each time. So then the sphere minus the collection of half spaces is equivalent to the ball minus the same half spaces. So it's a convex problem, and these papers use essentially the convexity of this space. Okay, so this is what's known for the spherical case. So what about when the space is the cube? So in this case, the rigorous results are pretty limited, and they're primarily at kappa equals to 0. So when kappa is 0, you can do this trivial calculation. So what is the expected number of elements in the cube that remain after I take away n times alpha half spaces? So I started with 2 to the n points in total. And then, of course, every time you put down a random half space, each point will survive with chance 1/2. So then the expected number is just exactly this thing. So once alpha is larger than 1, the expected number of points left is exponentially small. So with high probability, there will be no points. So the critical alpha, if it exists, it must be at most 1. So that's a trivial calculation. And then it was shown by these people that the critical alpha, again, if it exists, it must be strictly between 0 and 1. So more precisely, what they show is that when alpha is sufficiently close to 1, then with high probability the set is empty. And when alpha is sufficiently small, then with high probability the volume of the size of the set, it grows at least this much. So the exponent is 1 minus some constant times alpha. And this is not expected to be tight. And then finally, I want to mention this, the Kim and Roche lower bound. So actually, their lower bound is quite simple. So they just said, they actually said, we don't really care about the size of the set, and we just want to say that it's non-empty with high probability. So I just need to exhibit one element of the set. And it's just a sort of multi-scale majority algorithm applied to the matrix G. So the natural thing to do would be that you take your m by n matrix, and then you take a majority on each column, for example. So let's say you take each column and you take the sum, and you whether the sum is plus or minus, you just put that as the sign of your element. So that is going to almost work, but it doesn't quite work because you'll have made a mistake on a few of the entries. And so then the idea is to just fix it up by doing the same thing, but only in stages. So the first time you do the majority on the first like 90% of the columns. And then at the next stage, you use the next 90% of columns to fix the ones where you were a bit off, and so on. So that's the idea of their algorithm. Okay, so then, so the result I want to talk about today, it's a preliminary result for the same model. So for the Ising perceptron, also at kappa 0. So it's preliminary because we have a condition that we need to verify. So we have some explicit but somewhat complicated function, and we require that it be negative for all lambda which is not 0 or 1. So provided this condition, it holds for all alpha up to the predicted value, that the set is non-empty with positive probability, meaning that the lim-inf of the chance for it to be non-empty is strictly positive. So the method of proof, it applies for general kappa, but you would end up with a condition on some s of lambda that also depends on kappa. So I don't want to make any claim for general kappa. And then what is this function s of lambda? So this is what it looks like. So we can show analytically that it has a local max around 0 and a local max around 1, and then the condition is that it has to be negative everywhere else. It's not an extremely nice function, but it is a function of one variable, so in principle this may be verifiable numerically, but this has to be done. So for the rest of the talk, what I'll do is I will assume that this condition holds, and then I will cover some proof ideas for the theorem. Okay, so how would you get started? Well, so the expected number of solutions we saw is very easy to calculate, and we also saw that it's wrong. And in fact, it's wrong for any positive value of alpha. So as soon as I start putting down any linear number of half spaces, the yellow line is the exponent for the first moment. So it's just this 1 minus alpha log 2. So this is the expected number of solutions. But if the physics prediction is correct, then the blue line is the typical number of solutions. And for any positive alpha, the typical number of solutions, if the prediction is correct, it will be exponentially small relative to the expected number. Okay, so how can it be that the typical number of solutions is much smaller than the expected number? So it must be the case that the expectation is dominated by some rare event. So the expectation, I just put the arrow to emphasize that it's over the random matrix G. So the only thing that happens is that this expectation is dominated by some atypical G. And it's not hard to see that you can arrange for that to be the case, because it would make sense that you can favor for S to be large by taking the rows of G and making them a little bit more correlated than they normally would be. So I think it's not difficult to convince yourself of this. And then just to say a little more explicitly, you could imagine, for example, I could define this event that A epsilon is the event that the rows of G are like epsilon correlated with the all ones vector on average. So this is a rare event. It's not extremely rare. So the typical event is A0, and then you would think that the chance for A epsilon compared to the chance for A0, you would have a decrease of something like n times epsilon squared in the exponent, because this is the typical. But at the same time, you would expect a much bigger increase in the expected number, because once you make the rows epsilon correlated, it's much more likely that your set will be large. So you would expect the conditional mean of the size of the set to grow by a factor e to the n epsilon. so then what you would imagine is that this is the typical event. So hopefully if you take the expectation of the size of the set restricted to the typical event, this is probably going to be equal to the typical size of the random variable. But if you compare it with the expectation restricted to the rare event, because you would get such a big gain from the e to the n epsilon, this will be much bigger for epsilon small enough. And then this is upper bounded by the first moment. So this is a more explicit way, if you like, to explain that these two things can easily differ by a lot. Okay, so then, so if this is going to be the case, then sort of the obvious approach is that you would try to find some event which is typical. So you want the chance to that your disorder satisfies some property to be close to 1 or to be sub-exponential, but such that the random variable has very small variance when restricted to this event. And then more explicitly, what you would hope to find is that if I compute first and second moment conditioned on this typical event, you would be able to show that the second moment and the first moment squared are of the same order, and moreover that the first moment conditional is roughly the predicted value. So if you could do this, then you would be done, because this shows a concentration around the desired value conditional on some typical event. So then you'd be done. And then the whole problem is how would you choose this f? So f has to be restrictive enough to prevent s from being large. So you have to eliminate all the examples where you could think of where you make the rows a little too correlated or something like that. So f has to be somehow quite informative, but then the more complicated you make it, the more difficult it is to compute the actual moments. So you want f to be some kind of a minimal informative event. Okay, so then the question is how to choose this f, and the only goal for this f is that we reduce the variance of the size of the set. So then, so what actually is going to determine the size of the set? So to try to explain this, let me just take a different view of the same object. So this is just an equivalent depiction of the same instance. So I have a matrix G, which is m by n, and I will just view it as a complete bipartite graph. So the top row corresponds to the rows of the matrix, so there are m of these. And then the bottom row corresponds to the columns of the matrix, so there are n of these. So the bottom row are the variables, which are plus minus that you can choose, and then every square on the top row corresponds to one of the constraints. So and then there are weights on the graph corresponding to the entries of the matrix. So this is an equivalent object. So let me take this bipartite graph, and then imagine that you take x, which is a uniformly random sample from the solution space. So x is plus minus valued, and it's a random variable that lives on the vertices on the bottom level, and then let delta be g times x scaled by root n. So delta is the thing that's required to be positive, and delta lives on the top vertices of the graph. And then I want to understand what is the law of x and delta if I take a uniform sample. So you could imagine that you take this complete bipartite graph and you unfold it into its universal cover, which is a tree. And you could imagine that you say, well, let me try to approximate this very dense graph by a tree. So what that would mean is that suppose I take this edge here between a vertex, between the constraint A and the vertex I, and suppose I were to cut along this edge. So then in the unfolded version, I have this big tree, and I just cut one edge of the tree, so the two parts of the tree become disconnected. And then when I say that you want to approximate the original thing by a tree, I mean that the assumption is that when you cut the edge, the two parts on either side of the edge become independent because they're in different components of the cut tree. So once they become independent, on one side of the tree, this variable, it will have some law. Let's call it MIA. So I means it's associated to variable I, and the A means that it's sort of a message that points towards the constraint A. And then on the other side of the cut tree, this vertex has some law, which is, let's call it script D. Okay? And they're independent. And then if it's the case that all of these things are independent, then they should be related one to another by tree recursions, by Bayes' law. So these are the BP equations. For instance, the law of xi in this cut tree, it should be related to the laws of these vertices if you were to cut the edges that were below. So there are some laws associated to the directed edges, which are related by a series of equations. And then the important thing is that you can imagine taking this tree approximation and then folding it back, so gluing all of your edges back together to get back to the original model. So the key part I want to emphasize is that if you really believe that the tree approximation is a good approximation, then you should be able to calculate every time you fold an edge back or you glue an edge back together, you should be able to calculate how it changes the size of the model. So in principle, if it's a good enough approximation, you should be able to calculate the size of this set just in terms of all of these local variables from the cut tree. So that's the main thing I want to emphasize here. So when you, so that means that the solution to all of these, the recursions on this tree, it determines the size for the original model. If you believe that you have such strong correlation decay that your dense graph looks like a tree in some sense. Okay, so actually something even nicer happens conjecturally. So the belief is that in a dense graph, actually these tree equations can be simplified further into something called the TAP equations. So these are the references. So what is the idea of that? So you have all of these distributions which are indexed by directed edges of the graph. So I cut this edge, and then I have this MIA, which says it's the law of I when I cut the edge that goes to A. But this is it's a really dense graph, so it's not the case that I has 3 neighbors. I actually has order n neighbors. So the point is that because each vertex has so many neighbors, it shouldn't be that removing a single one will affect it very much. So essentially, all of these MIAs should be pretty much the same because each individual interaction is so weak. So then you would expect that xi in the cut graph, it's a Rademacher plus minus law with mean MIA, where MIA is pretty much just one value MI, not depending on A, with a tiny random correction which does depend on A, but is of smaller order. And likewise, when you cut the edge IA, this delta A, it should be some other distribution with a parameter NAI. Sorry, this should read NA. So it should be essentially one parameter NA that depends only on A plus a smaller order correction. So actually, if you take this and then expand the BP equations out, it turns out that these simpler parameters, so these MI and the NA, they will satisfy a closed system of equations, and the small corrections will disappear. And these are the tap equations. So I'll just comment that the main term here, it's sort of the naive term that you would expect. And then this minus bn, or the minus dm, it's a correction essentially, which accounts for the fact that when you take g times m, what you really want to do is you want to take g times something like this. And then there will be a small correlation between g and the epsilon. So the correlation between g and epsilon, it's subtracted in these terms here.
So is that called the Onsager correction?
This is not, yeah, this is Onsager correction. Okay, so then, so in a dense graph, the BP actually simplifies very nicely to these equations, which I'm going to abbreviate further. So these are the tap equations. So this top line here, I will abbreviate it as R. And then this bottom line here, I will abbreviate as T. So you just have two equations, and they relate to these parameters M and N. And then finally, the tree approximation for the size of the model, it also simplifies in the dense limit. So instead of having a function of these messages indexed by directed edges, it's just some explicit function which is of these vectors m and n. Okay, so then, so this whole story, if you believe it, it would suggest to you how you should choose an event to condition on. So again, you have this random set S, and you take a uniform sample from S, and then this is the thing that is supposed to be positive. And then according to the tap approximation, the x variables, they behave like a Rademacher with mean m, and the delta variables, they behave according to some other distribution with parameter n. And the m and n vectors satisfy some recursive relation. And moreover, if the correlation is strong enough, you would imagine that the size of the set, it's approximated by this tap formula. So this is the tree formula, plus some very small error. So you would hope that if everything decorrelates very nicely, then when you fold back the tree to make the original graph, the error here will be from correlations between the two endpoints when you join up an edge. So if you hope that there's sufficiently small correlation at each step, you won't accumulate too much error here. So this is the big O of 1 is sort of the best you could hope for, I think. And moreover, these two things are both random quantities. They have a very small error relative to one another. And then they would have a somewhat larger error relative to the explicit limit. So g of alpha is some constant. It's what the physicists predicted as the limit of this model. And you would think that m and n have some fluctuations. So here, probably the best you can hope for is order root n fluctuation. So from this whole story, it would very strongly suggest that if you want to do a moment method with some conditioning, you really need to fix these m and n. Because if you just look at the fluctuations of m and n alone, this is probably going to account for the square root n fluctuations. So it seems that you really have to fix those. And then it's natural to ask whether this would be enough.
But the square root n fluctuations, they're not problem by themselves for the second moment method, right?
So they're probably like Gaussian type fluctuations. So if you were to take the first moment, this will become an order n error in the, yeah. So it won't work, I think. Okay, so then once we got to this point, we imagined the following calculation. So this is not really the correct thing, but this is like an idealized version of what you would try to do. So this is the natural thing to do, right? You fix some typical realization of the m and n vector, and then you just condition on your Gaussian matrix satisfying the tap equations relative to the m and n vector. And the very nice thing about the tap equations, which are again here, is that these are, if m and n are fixed, these are linear constraints on the matrix G, which is Gaussian. So in principle, you can do all of the calculations because it's just it's linear constraints on a Gaussian random variable. So it should be very tractable. And then, since we're trying for a lower bound, we can also restrict the space to help us. So we thought, let's take the space that we're interested in and restrict it to, this is a sort of a spherical band which is centered around the m vector, which is supposed to be the mean vector. So this is a nice slice of the space to work with. And then in this sort of imaginary scenario, you can actually do out all of the calculations, and what you would find is that the second moment and the first moment squared are indeed comparable. And what is the conditional first moment? It actually corresponds exactly to the tap formula from the tree approximation. So we thought this was quite promising, and this was how we started our project. But then there's an obvious logical flaw in this whole thing, which is that it's actually not known if the tap solution exists or is unique. So then, since this is not known and seems difficult to prove, it doesn't make any logical sense to condition on a typical solution, whatever this would mean. And it doesn't make sense to say that G should just be Gaussian given these equations, because we don't know what is the correlation between G and M and N. We don't even know if they exist, but if they exist, we don't know what is the correlation. So we thought that this calculation was probably not complete garbage because it gave this nice formula, but it was clear that this thing fundamentally doesn't make sense. So then a way to fix it is to approach it iteratively. So actually we'll use something else that is known, which I'll describe, which is to take the tap equations and make them iterative. So put time indices as follows, and run the tap equations from some deterministic starting vectors. So if you do that, then every time I run the equations, I don't reveal anything extra, right? It's not like I look around at the other entries of G. The only thing I reveal at every iteration is that I reveal the projection of G onto some vector that I found before. So that's all I will reveal. So if I run the tap prediction for, say, t steps, then it is actually true that G will still be Gaussian given the equations that I wrote down along the way. So at least this part will make sense. And then the other thing, which is very nice, is that these people analyze this iteration, and they found that it converges in some weak sense, which is that if you run it for long enough time, then the difference between the two successive iterates in L2 will be small. So then the natural thing to do would be to try to condition on this tap iteration instead of conditioning on a fixed point that you don't know about. Actually, this was done in an independent work of Erwin Bolthausen, where he took essentially exactly this scheme and he applied it to the high temperature SK model to compute its free energy.
Compute of the lower bound.
He actually computes the free energy. So
So far you only described lower bound, right?
Right, so we restrict, we truncate the space, so we only get a lower bound. So he actually does not truncate, so he gets both directions. But it's not clear if it works in the full high temperature regime of SK. Okay, so it suggests that this method is somewhat promising. So we essentially follow the same approach, but then there is some problem, which is that we work at 0 temperatures. So there is some delicate point that I want to talk about, which is that if you want to prove anything at 0 temperature by the moment method, you have to get your results quite precise. So if I were at positive temperature, the error that I would need between the second moment and the first moment squared, it would just be anything that sub-exponential will do. But at 0 temperature, to get anything interesting, you need this error to be within a constant vector. So in order to have these within a constant vector, it actually only works if you have an exact tap solution. So we tried many versions where we don't have an exact one, and it just seems that it will never match unless you have an exact tap solution. So then we thought, let's try to fix it by somehow engineering something that looks like an exact tap solution, even though we don't have one. So this is something that we found which seemed to work, which is that I ran the tap iteration for t steps, so I should be approximately at a tap solution. So nt and nt minus 1 should be pretty close. So we thought, why don't you just solve 1/2 of the tap equation? So find a fixed point for 1/2 of the equations, and then take another projection onto this fixed point. And then use this to define the space that you truncate on. And somewhat surprisingly, we found that this actually seems to work. So if you create this sort of pseudo fixed point like this, it turned out that the second moment and the first one squared are indeed comparable as you wanted. And so because of all these sort of odd truncations that happen, you lost a little bit in the first moment, but not so much. So it's still pretty close to the physics prediction, and you can get there by taking a limit. So we thought, okay, this seems great, and it seems to work. And then there was one last issue, which is that it really requires to solve this equation exactly. And it turns out that it can only be solved if all of the entries of this vector are strictly positive. So this was the last issue that we had to deal with. So this is the construction. The construction is that I will take the original problem, so I will rename the original matrix G hat, and I will break it up into 2 pieces. So one is the majority of the matrix, and then I will just save a few columns on the right to do with some extra. So the main part I will treat essentially as before. So take the main part that you broke off and run tap, but only on this the main matrix. So if you run tap for t steps, you're going to get some iterate mt. And then if you apply g to mt, I claim that it will be mostly positive. Because if you run tap for many iterations, you will be close to a fixed point. And then what is the fixed point representing? It's representing the mean of your solution space. So certainly the mean of the solution space will satisfy that g times it is positive, because that's the definition of the solution space. So if you run for enough steps, it should be mostly positive, except for some small fraction epsilon t of entries, where epsilon t goes to 0 with t. And now we're going to assume that the parameters are chosen such that the width of this last part, it should be very small because we don't want to lose too much, but it should be very large relative to this error that we made. So then what can you do? The point is that if epsilon is very large relative to this the error from the tap equations, then you could consider what if I try to choose plus minus signs for the last few columns, such that this last matrix times the plus minus signs, it will be strictly larger than minus g times mt. And the point is that you can choose epsilon as large as you want, as long as it's very small relative to 1. So if you choose epsilon large enough, then you will have a lot of room within the columns relative to this very small error that was made here. So it should be the case that if epsilon is big enough, then this thing should be another perceptron. It's a perceptron with n epsilon coordinates, and it should be very subcritical because you chose epsilon that way. So if you have a perceptron that's very subcritical, you don't have to do something very fancy to find an element of it. So one thing that you can do is that you can take this majority algorithm from the Kim-Roach paper and adapt it to this setting to show that it contains some element with good probability. So with good chance, this thing is not empty. And if this is non-empty, then you can plug it back in here. So then g times mt plus e times the element of this perceptron, it will be strictly positive. And based on that, you can solve for an exact fixed point. And now you're done because you can do a modification of the original perceptron model, which is just a restriction. So instead of looking for the perceptron solutions of g hat, I'm going to look at elements which are an arbitrary vector on the first n coordinates, but I will just restrict it to agree with the special element z star on the last few coordinates. And then the new constraint will just be that this thing will be strictly positive, so this will certainly be a subset of the original perceptron, so it's enough for a lower bound. So the second moment that we finally do is based on this object. Okay, so then I will finish with just some remarks. This function s of lambda that we have the condition on, it just comes from calculating the second moment from pairs that are at a specific distance in the space. So remember that we always make the restriction that we're in a sort of spherical band around the m vector. So the s of lambda, it comes from two elements which are both in this spherical band around the m, but which are at an angle corresponding to lambda. So that's this s lambda function. So then it's natural to ask about whether you can prove a matching upper bound. So the work of Erwin Bolthausen for the SK, it would suggest that if you consider an unrestricted moment method, you might be able to prove a matching upper bound, but it seems rather difficult. So our result is with positive probability. So I think it would be an interesting question if there is some general Friedgut type lemma for a general class of models that includes this one. And then something else which our result doesn't approach, and I think is not really known for any model, is whether the tap approximation is valid, meaning that the size of the set and the tap formula should be close to a smaller error than just to the replica symmetric prediction. So the tap formula is a random quantity, and it should actually be a better approximation than just the mean value. So a more recent work by these people, they considered a different model where you symmetrize it. So we always cut a half space going on one side. So you can consider if you just cut both sides of the space. So this is certainly easier to analyze, but in principle you may be able to prove more finer properties of it. So I think this may be a quite attractive model. So I never said anything about the case of the spherical perceptron where kappa is negative. So there's very little understood rigorously about it. And there are some recent physics works that study this model. And then finally, there are interesting computational questions about the perceptron because, for instance, the Ising perceptron for sufficiently large alpha, the space of solutions is very disconnected, so it should be quite difficult to find one. But there are some physics works that suggest that it has some interesting underlying structure. And that's all. So thanks very much.
When you refer to high temperature work at 2000, and so is that still in the context of perceptron model?
No, for high temperature SK.
SK.
Yeah.
Just one.
Yeah, I
is
think.
there a version of the positive temperature, interesting version of the positive temperature model for the perceptron model?
Yes, Talleyrand also has a paper on it for high temperature.
For the perceptron model.
Yeah, so it would just be e to the minus beta times the number of constraints violated.
Number of constraints violated.
So if you apply Stochastics method, Gaussian comparison, it also probably gives you a lower bound on the.
So it gives an upper bound, which is 2, I think, or no, it's a little better than 2, but it's not the correct one.
For the Ising.
For the Ising, I think it gives an upper. I checked. It gives an upper bound, which I think is.
Lower bound on log G, but yeah, okay. So and is it?
So it gives an upper bound which is larger than 1, which is the trivial
Okay, so
upper bound.
Okay.
And the lower bound is a direction that doesn't work because yeah. So.
But actually, like in your last step, when you use the subcritical,
Uh-huh.
did you use the Gaussian this comparison instead of KR algorithm?
For a lower bound?
You just want the existence of solution, right?
Yeah, that's true.
So I thought that this is what Stochastics showed, right? That with high probability there exists a solution. I mean, but not in a very sharp way. Am I wrong? Or?
But he shows it for the spherical model.
No, but you can do it for Ising as well.
For a lower bound?
For the existence, right? Anyway, so we can.
Yeah, I think not, but maybe we can discuss afterwards.
So not lower bound on the threshold, just probability that there exists a solution, right? It gives you a lower bound on this. I thought. I don't know if I'm wrong.
I thought it doesn't, but maybe we should discuss. So, yeah.
So at least one of the bottlenecks was you don't know existence and uniqueness of the solution of the TAP. Does anything that you did tell you anything related to existence and uniqueness of TAP, or not?
No, I mean, no, I don't think so. Certainly no one thinks that there are multiple solutions, and everyone thinks there's a unique one. But I think that's already strongly suggested by the fact that if you just start at like the all ones vector, you will converge to a solution. So.
Actually, just one last question. So for the upper bound, can you use some kind of interpolation?
No, so it's exactly a method that does not, the standard interpolation method doesn't apply.
Okay.
Yeah.
So nobody's tried. I mean, so
many people tried. I think it doesn't work. Yeah.
But they weren't Russian.
I think some of them were.
Some of them are Russian.
Okay,
Let's thank Mike again.